So this video introduces Taylor's remainder theorem in Lagrange form. So our very last question that we have to answer is, suppose that a function has derivatives of all orders in some kind of open interval containing the number a. This then allows us to generate a Taylor series generated by f centered at a. Let's just pretend that it converges for some meaningful interval of convergence and look at the intersection between the domain of the function f and the interval convergence of p. Under what conditions can we say that these functions are actually the same thing? That the function is equal to its power series generated at f centered at a. To tackle that question, here is Taylor's remainder theorem, at least Lagrange form. There's multiple ways to write this theorem. So suppose you have f is a function that's differentiable through all orders up to n plus 1 in an interval containing I. For every single x and I, define the remainder function as the difference between the function and the nth order Taylor polynomial generated at f by f at x equals a. Now for every such x in the interval, there's always a value c that's between where it's centered and where you're evaluating the function, so that the difference between the function and the Taylor polynomial, which is called the remainder term, is given by this particular product. Now, if you look at that result, it looks pretty awful, but if you replace the n with 0 and then solve for f of x minus f of a over x minus a, you get just the mean value theorem. I welcome you to try it. The proof of this is pretty involved, and for that reason, I'm going to put it at the very, very end. A lot of times, really bad proofs, I just move on. But this is one of those results that is so important that you should see a justification for it. But then again, that'll be at the end. So let's just use the theorem and see what it says. I want to know, if you have the function f of x equals e to the x, and I evaluate that function at 1, of course we get the value of e. But instead, I'd like to use the Maclaurin polynomial of 5th degree and evaluate that at 1. And I'd like to know then, how close is it to the value of the function at 1? Well, a Maclaurin polynomial is just a Taylor polynomial centered at 0. So we can use Taylor's theorem with remainder in order to go and approximate that. So the difference between the function and the polynomial, 5th order at 1, it's called the remainder term, evaluated at 1. But Taylor's theorem says that that is equal to the 6th derivative of the function, evaluated at c, over 6 factorial times 1 to the 6th. Now, notice, see how the subscript for r is 5, and how everything is a 6 power, 6 factorial, 6th derivative. That was the connection we have in the theorem. But we remember, though, that the derivative of e to the x is just e to the x. So if I evaluate the 6th derivative of the function and evaluate at c, you just get e to the c. And that's where c is between where it's centered, 0, and where I'm evaluating, 1. So c is just between 0 and 1. So an absolute value, the overall error then between the function at 1 and approximating that value by evaluating this Maclaurin polynomial at 1, that would be equal to the absolute value of e to the c over 6 factorial, which is just that because it's positive. But we know that e to the c, it varies as c changes, but c can only go from 0 to 1. And we know the function e to the x is increasing. So the largest that e to the c could ever be is just e. And since 6 factorial is 720, we get that the overall difference between the function and our approximation at 1 will be no more than 3 divided by 720. That is 0.0042. So that's a pretty darn small error. And in fact, if you just look at the actual difference, look at the function value and look at the actual polynomial and just subtract them, the actual error is less than that. It's only 0.002. Let's reverse that question. This time I'm going to give you the error, and I want to know what degree polynomial will result so that the difference between the sine function at 3 and the polynomial of this degree at 3, that difference will be less than 0.001 in absolute error. So we need the Taylor series for the sine, which we've already done. Here is the corresponding Taylor polynomial. Notice that I'm expressing the power in terms of 2n plus 1 because the powers are all odd. I'll need that when I talk about the remainder term. So the remainder term then, when you use the subscript, it should refer to the degree you go to. So the degree you go to in the polynomial is 2n plus 1. So the remainder term, evaluated at 3 by Taylor's theorem in Lagrange form, would then be equal to, in absolute value, it'd be the derivative of the function f, the sine of x, but it would be the 2n plus 2 order derivative. And then you have to evaluate that derivative at c, put it in absolute value. And it's still all over the 2n plus 2 factorial times 3 to the 2n plus 2. Notice the 2n plus 2's, see how it's all more than the index for the remainder. The remainder is 2n plus 1. Everything else here is 2n plus 2. And the c is somewhere between 0 and 3. Now that derivative looks really pretty bad. But since I'm looking for the absolute error, so I put in absolute values, remember that the derivative of sine, no matter how many derivatives you take, are either sine, cosine, negative sine, or negative cosine. So an absolute value, that's either the absolute value of sine or the absolute value of cosine. And in that case, I don't care what c is. If I evaluate either of those at any number, the result is always less than 1, or equal to it. So I can then say that that remainder, no matter what happens, will be less than that fraction. Notice that means that now x and the function are no longer present. I can just evaluate that function as n grows. Now, a factorial grows faster than a power. So this thing has to go to 0. So all I did was evaluate that expression that you see for x is 1, 2, and 3, but the x in the form is actually n. And I looked at the corresponding error term, which is the y sub 1. So when I get to when n is 6, the error is less than the 0.001 that was required. So if n is 6, the degree of the polynomial is 2n plus 1, that's 13. So if I go to the 13th degree polynomial, Maclaurin polynomial, and I evaluate it at 3, and I evaluate the sine at 3, the error is going to be less than 0.001. In fact, it's a lot less. Also, if you remember, it's hinted that if you move then the evaluation of 3 closer to the center of 0, the error gets less. If you remember my graphs I did before. In fact, what you see in front of you, that's the graph of the sine of the function, the sine of x, and also the polynomial of 13th degree, which is found by forming the polynomial, the Maclaurin polynomial, generated by the sine function at 0. The graphs are identical. They're pretty much the exact same thing. Now, don't think that the sine's a polynomial. It's not. It's just really, really closely approximated by 1, as long as you're between 0 and 3. That means we're getting really close to answering the question, when does the power series generated by a function, when would it actually equal the function on some interval? Let's go back to the definitions we know. Here is the Taylor series of the function generated by f centered at a. But it's a power series. So we know that if that series converges, it's only true if the limit of the partial sums converges. Now this is for every single choice of x in a certain interval. But the sequence of partial sums, that's just the summation to a point. In the series, that's just the Taylor polynomial of that degree. But we also now know, because of the definition I gave you, that the Taylor polynomial is actually the difference between the function and the remainder. But then in the limit, f of x, that's just a number. The n's not changing there. It's just a number. So you just bring the limit through. So then the series has to equal, if it equals anything, the function at x minus the remainder as n increases without bound evaluated at x. So, provided that remainder is 0, you have to then get that the function is equal to its series. And not only does it equal it, but of course the series has to converge. So let's look at an example. Let's look at the Taylor series generated by the sine function expanded at 0. Once again, here's the formula. Notice how the power on x is to the 2n plus 1 because all the powers on x are odd. But remember that it doesn't matter what derivative of this function you take. The derivative is always plus or minus sine or plus or minus cosine. So in absolute value, that would then mean that f to that power, doesn't matter what the alpha power is going to be, that's evaluated any way you like, is always going to be less than or equal to 1. But the remainder that corresponds to the polynomial of order 2n plus 1, that would equal the derivative of the function, where you take it to the 2n plus 2 power, evaluate at some c, all over 2n plus 2 factorial, times x to the 2n plus 2 power. But the derivative is just less than 1. That gives you then this fraction, that the remainder then has to be less than or equal to the absolute value of x to the power of 2n plus 2 all over 2n plus 2 factorial. Now, x is a constant, remember, because the limit is as n grows. So x is a constant. Because of that, you have a exponential where the power is increasing, divided by a factorial where the input to the factorial is increasing. Well, factorials grow faster than exponentials. So eventually, that fraction has to go to 0. That shows then the remainder term, no matter what x is, always goes to 0. That means that the sign has to be the same as the power series. They're exactly the same in every way. This is a great result. Now, if we wanted to, I can go back through and verify a lot of these results, but instead it's probably better just to state them. For example, I just convinced you the sine of x is given by a power series. From that, remembering our rules about power series, I could easily get a rule for cosine. I would just take derivatives of both sides. E to the x also very easily could show you that e to the x has to converge to the power series it generates. I've already hinted that 1 plus x to the kth power being equal to that binomial series, I hinted that they would converge to the same thing on the interval from -1 to 1. That's one of those I'm not going to prove, though. But 1 over 1 minus x is equal to that power series because it's just a geometric series, and we already know that one's true. Many of these are not difficult to do. The logarithm's not difficult to do because of the geometric series, and the arctangent and the arcsine are not difficult once we have the binomial series. So these are all series that you should use to manipulate. You're not expected to memorize them, but probably use them a lot. You will anyway. Well, that's a basic introduction to power series and when does the power series equal the original function. So we can go through a lot of examples now. So the next couple slides I go over a few, but at the very end there's a proof of Taylor's remainder theorem in Lagrange form. If you don't want to look at that, you don't have to. You can just stop when I get to that point. There's nothing after that that you would really need. It's only for completeness and also for those of you who want to know kind of why. So here's one example. The Taylor's theorem with remainder can be used in order to prove a lot of the things we saw back in Calc 1 that I never really did bother to do so. For example, when does Newton's method work? The second derivative test didn't really explain that completely. So let's go do that now. I'll do a slightly easier version though of the second derivative test. Suppose f is a second order continuously differentiable function. So it has a second derivative and that second derivative is continuous. Just on some interval containing a, and that the first derivative at a is 0. If the second derivative at a is positive, then f of a is a relative min. If the second derivative at a is negative, then f of a is a relative max. I'll just prove one of them. Suppose that the second derivative at a is positive. Notice that since the second derivative is continuous, that implies then that the second derivative at x will approach the second derivative at a as x approaches a. Also, remember, I'm assuming that f prime of the second derivative of f at a is positive. So these two things together mean that as long as x is near a, like c is, then the second derivative of that value would be near the second derivative at a, which is positive. So I can then say in the limit, getting close enough, that I can then say that the second derivative of the function at c should be positive, as long as we get close enough. So, by using Taylor's theorem with remainder, for x really near a, f of x has to equal the Taylor polynomial of first degree. That's this guy right here. That's the polynomial. And then you have over here the remainder term. Well, if you look at it though, don't focus in on so much on the middle portion of the polynomial, because this middle piece will be 0 because remember the first derivative is 0. So the Taylor polynomial at a to the first order is only f of a. But also, if x is near a, of course this portion is positive because it's being squared. And I know if x is near a, that this is positive anyway. So this term is positive. So I'm taking f of a and I'm adding something positive. It's clearly then greater than or equal to f of a. This then shows then that if f of x, if x is near a, then f of x is more than or equal to f of a. So f of a must be a relative min. That's the proof. Now what's really neat is that the argument I gave you, you can extend it out to however many derivatives you want. So you get what's called the nth derivative test. Suppose f is an nth order continuously differentiable function. So it has derivatives of all those orders and they're all continuous on some interval containing a. Also assume that the first derivative all the way up to the n minus 1 order derivative at a is 0. Then if you just look at the Taylor polynomial at a, the only thing you have left would just be f of a, because all the other terms would just be 0. They'd all be gone. If you look at if you have that the nth derivative of f at a is positive and n is even, then using the argument I just gave you, you'd find that f of a is a relative min, because the function would have to be larger than or equal to f of a for x near a. If n is even and the nth derivative of f at a is less than 0, then you'd get that f of a is a relative max. Also, a really neat result is if n's actually odd, you won't get a relative max or a relative min, but you will get an inflection point because the function has to be bigger than the value on one side of a and less than the value at the other side of a. So it's got to be a turn of some kind. And if you want to do that as an application, if f of x equals x to the fourth, notice that the first, second, and third derivatives are all 0, but the fourth derivative is 24. So since the fourth derivative is positive and n is even, that means then f of 0 equals 0. That's got to be a relative min by the nth degree, in this case, fourth degree derivative test. So let's begin our proof of Taylor's remainder theorem. Assume that f is differentiable of up to n plus 1th order in an interval containing a. Let's just pick x in that interval, and we'll define the constant k to be the one value that would satisfy this particular equation. Remember now, x and n are both fixed, and a is fixed, so the only thing you don't know is what r is, and it's determined by this particular equation. Now, I'm going to prove then that r is actually equal to the nth plus 1 derivative of f evaluated at some c, where c is between a and x, divided by n plus 1 factorial. Just recall that the Taylor polynomial at a is defined to be so that if you take the kth derivative of f and the kth derivative of p and evaluate them both at a, you have to get the same answer. And that's true for really any kth derivative from the 0th derivative up to the nth. To find a new function, which would be the difference between the function and the Taylor polynomial and that remainder, I'm going to show that this function actually equals, its nth plus 1 derivative is actually equal to 0. And that will then give us our result. So here's that function again that I'm going to use in order to get the result I need. Notice that if you just plug in x, by definition, r was picked so that this was 0. Obviously though, if you just plug in a, f of a, and the Taylor polynomial of nth degree at a, those two things are the same thing. So that's 0. And a minus a, of course, is 0 to a power. So that whole thing is 0. So since f of x and f of a are both 0, by the mean value theorem, specifically the simpler form, Rolle's theorem, there is a value c1 between a and x so that the first derivative of capital F at c1 is 0. Oh, let's do that again, but this time let's focus on the first derivative of this capital F function. Now if you take its first derivative, you would get this. But notice if you plug in a everywhere, the first derivative of little f and the first derivative of the Taylor polynomial of the nth degree, If you evaluate them both at a, they're the same value. So that first subtraction is 0. And of course, at the end, a minus a is 0, and 0 to any power is 0. So this whole thing adds up to be 0. But I also have this c1. So at the first derivative of this capital F function at c1 is also 0. So since the first derivative of f at a and c are both 0, I can use the mean value theorem, or Rolle's theorem, to show that there's a c2 between a and c1, so that the second derivative of this capital F function at c2 is 0. Just continue this process over and over and over and over again up until the n derivatives. You'll then get a sequence of things. The very last one then that matters is that the nth derivative of f at cn is 0. So as I said, let's do it one last time. Here's the function that we're using in order to get our result. Let's take its nth derivative. So let's nth derivatives of everything and evaluate everything at a for the same reasons as before. The original function little f, its nth derivative evaluated at a, and the Taylor polynomial, its nth derivative evaluated at a, they're equal. So that subtraction is 0. And then at the end, if you take n derivatives of t minus a, you'll still have a t minus a factor in it. So when you plug in a for t, you'd get a minus a, that's 0. So the nth derivative of this function, capital F, evaluated at a is 0. But we know already from previous slides, and by doing the process over and over and over again, that the nth derivative of f evaluated at some cn, where cn is between a and x, that's going to be 0 also. So by the mean value theorem, or Rolle's theorem, there is a value c between a and cn, and that means c is between a and x. So that the nth plus 1 derivative of the capital F function evaluated at c would be 0. But if you take n plus 1 derivatives of capital F function, you'd wind up taking n plus 1 derivatives of a Taylor polynomial of degree n. Well, that's too many derivatives. That would just go away entirely. And if you take t minus a to the n plus 1 power and take n plus 1 derivatives of it, the only thing left then is the constant r, and it have n plus 1 factorial. When you evaluate that all at c, you have to get 0. Notice that's an equation that involves r, the unknown constant. If you just solve for r, you get the result that I said we would get. That then proves Taylor's theorem, the remainder form, in Lagrangian form.